All righty, welcome to lecture 4. So we are going to conclude the cardiovascular system with talking about regulation of blood pressure. All right, so we have talked about what makes up the cardiovascular system. We've talked about the heart, we've talked about the vessels, and we've talked about the blood. The important question is how all of that functions together. So what is the main function of the cardiovascular system? It is to service the body tissues, delivering good things and removing bad things. In order to do this, the body has to maintain appropriate rates of blood flow, and we call that blood pressure. So the first component of blood pressure that I'm going to introduce to you is called cardiac output. This is the volume of blood pumped through the heart in 1 minute. Okay, so this is the calculation. It is the combination of stroke volume and heart rate. Stroke volume is the volume of blood in milliliters that is pumped per heartbeat. And then the heart rate is the number of heartbeats. All right, so stroke volume times heart rate. So milliliter per beat times the number of beats per minute will give us cardiac output. All right, so sometimes through my presentation, you'll see me using cardiac output and blood flow interchangeably, all right? But you should understand that the milliliters per beat of the heart, or the stroke volume, and the heart rate, or the number of beats per minute, both contribute to the cardiac output, which is the blood flow. All right, so remember, blood always flows from high to low pressure, all right? So when we're in the heart, the blood pressure is at very high levels. As we go down into the arteries, the arterioles, smaller vessels through the systemic system here, blood pressure is going down. I've talked about this before with venous return, how that pressure needs to be very low in the heart in order for that blood to re-enter the heart. Then that becomes pressurized again as the heart pumps it into the lungs instead this time, and then through the pulmonary circuit back to the heart. All right, so pressure, you'll notice throughout this presentation, is measured in millimeters of mercury. All right, this is just a basic unit of pressure that is exerted by a column of mercury to at 1 millimeter high. All right, so it's just don't worry about exactly what that means. Let's just call it an arbitrary unit of pressure. All right, there's also atmospheric pressure, or ATM, and that is equivalent to 760 millimeters of mercury. So let's talk about flow rate. So flow rate mechanics. What determines flow rate? There's two factors: a change in pressure, or the pressure gradient. All right, so this is known as delta P, or that triangle indicating delta, indicating change in P pressure. And then the other factor is the impediment to the flow, or the resistance. All right, so this is termed with an R. All right, so there is an actual formula where we can calculate blood flow, which is the change in pressure over the resistance. All right, and this is known as Ohm's law. So blood flow is directly proportional to the pressure difference in that vessel, but inversely proportional to the resistance in the vessel. All right, so think about this. The change in pressure, if the change in pressure is high, the flow rate is going to be high as well, directly proportional, right? So if high pressure over here, low pressure over here, the difference is large, then the flow is going to be faster. However, if there's more resistance, the flow rate is inversely proportional to that. So more resistance, so whether that is constricted vessels, longer vessel length, whatever that is, decreases the flow rate because there's more that is impeding the flow. So what happens if we change the pressure? So if the pressure gradient is changed, there's a few things that make that happen. All right, if we increase the flow rate, so that can happen naturally during exercise or during stress or fight or flight responses. So that might increase flow rate because our body is demanding higher flow so that the body tissues can be nourished at a faster rate. or if we increase the resistance. So I mentioned this a little bit on the last slide, but this could be a longer vessel length or a decrease in the vessel diameter, vasoconstriction. But what we're going to talk about more so is a buildup of plaque, or this is termed arteriosclerosis. This is a bad thing. There's also an increased blood viscosity that can be caused by an excessive number of red blood cells. So there's various things that can change the pressure, all right? So if you increase the flow rate or if you increase the resistance, that will change your pressure, all right? So we can think about this mathematically again by just flipping our equation, that the change in pressure is equivalent to the flow rate times the resistance, all right? So a change in cardiac output or resistance is ultimately going to change this factor right here, which is pressure. So remember, the main function is to service the body tissues, deliver the good things, remove the bad things. We need to regulate blood pressure in order to make sure that at specific times when we need it, that there is an increase in cardiac output so that our tissues get the right amount of blood. So how does the body sense pressure? We have natural mechanoreceptor neurons that are stretch sensitive that are called baroreceptors in our body. They are located mostly in the carotid and pulmonary arteries, as well as the aorta and various areas of the heart, the right atrium and right ventricle mostly. All right, so the slide is a little bit busy, but I've highlighted the main important things for you. Arterial baroreceptors is one type of baroreceptors. Then there's cardiopulmonary baroreceptors. These are different based on how they sense pressure based on their location, all right? So arterial, so these are going to be in your arteries, so pulmonary arteries, carotid arteries, or the aorta. So they sense high pressure, right? These are high pressure areas. This is where blood is exiting the heart and going either to the lungs or to the rest of the body. So they sense the stretch in the vessel, which is related to the pressure, all right? The pressure change increases the nerve impulses that are sent eventually to the brain, which ultimately can regulate that pressure then. How this works in the heart, these cardiopulmonary baroreceptors, instead of sensing stretch in a vessel, they're sensing low pressure. They sense the blood volume, all right? So they're mostly going to be in the right atrium and the right ventricle. There are some of these cardiopulmonary baroreceptors in the pulmonary arteries as well, because these are the lower pressure areas, all right? So they're going to sense blood volume rather than the stretch of the vessel itself, all right? So the sensing is called the baroreflex, all right? So the sense of that stretch from the mechanoreceptor neurons is sent to the brain. The brain ultimately then regulates pressure, all right? So this loop, it's a negative feedback loop, right? So more stretch or change in pressure that's sensed, the more that feedback is sent to the brain, and then pressure is down regulated, all right? So high increase in baroreceptors indicates a downregulation of pressure, all right? That's why it's a negative feedback loop. But this is very, very fast, all right? So this can complete before a cardiac cycle has been completed. So it takes seconds to minutes for the baroreflex to occur. So because they're activated by blood volume or stretching of the arterial walls, they then send signals to the brain. The signals to the brain are sent to the arteries in the heart to reduce blood pressure. Those signals are sent from the brain to those areas. They can regulate vasodilation, reduce the cardiac output, or increase the water or sodium excretion in order to modify pressure, all right? So if there is an increase in vasodilation, the increase in the vessel diameter, then you can decrease the total resistance or the total pressure at that artery. Similarly, if you decrease cardiac output or increase urination, you can do this by decreasing the venous return, right? So the less blood that is coming back to the heart, the less amount that is needed to refill the heart, and so you can lower that cardiac output. You can also increase urination, which helps to just reduce the overall blood volume, because in the blood lecture, as I told you, 90% of the plasma, which makes up 55% of the total blood content, is made of water. All right, so getting rid of some of that water will get rid of some of the blood volume. So increasing the flow, decreasing the flow, and also decreasing the resistance ultimately results in a decrease in pressure. So how do we measure blood pressure? So I'm sure you have gone to your general practitioner, you've sat in that doctor's office, and you've had your blood pressure taken. You've probably heard the terms systolic and diastolic blood pressure. Do you remember from the cardiac lectures, systole and diastole? That's where these terms come from. So we can measure the pressure on the arteries during diastole and during systole. So during diastole, when the heart is refilling with blood, and during systole, when the blood is forced out of the heart. All right, so systolic blood pressure is the peak pressure. It's produced by the ventricles contracting, right? So systole, where the heart pumps the blood out, this is going to be a measurement through the arteries of a high pressure, right? They're getting a lot of blood pumped out into those arteries. This is the peak of the pressure. This is generally a healthy range around 120. So if you remember systolic or diastolic blood pressure, you think 120 over 80. Diastolic blood pressure measured during diastole, this is the baseline pressure. So the ventricles are relaxed, the blood is refilling into the heart, and those vessels where you're measuring the pressure is releasing because there's not a ton of blood that's being pumped out into them, right? Okay, so the normal range for diastolic blood pressure is around 80. You measure this by actually restricting this vessel here. So you put the cuff around, generally when you're doing it to a human, you can do this to animals as well. You put the cuff around and you pump the pressure up above 120. Then when you're measuring that pressure, you're measuring it between the 120 and the 80. And once it goes down below 80, then the cuff fully releases that vessel, and that vessel is able to fully push blood through. All right, so when things go wrong with blood pressure, you can have either too low, this could be due to blood loss or dehydration, not enough water in circulation. You could have blood pressure that's too high. Generally, this is the most common problem. When blood pressure is off, it's normally too high, all right? So this is generally when the baseline pressure is high, even when it's supposed to be low, all right? So this could happen from decreased vessel diameters due to plaque buildup. I had mentioned this earlier. This is termed arteriosclerosis. You could have increased blood volume. This is due to high sodium intake. So you can probably recognize with specific diets, poor diet, that can often lead to high blood pressure. It's because of the sodium. Or chronic stress. So there's a sympathetic nervous system activation that's chronic. So your body is constantly in this fight or flight mode when there's actually no tiger to run away from, all right? So you're trying to increase blood flow all the time when there's really nothing to actually take up all that blood and use it, and that can lead to chronic high blood pressure. So this prolonged high blood pressure is termed hypertension. This will endanger cardiovascular health. So you might be wondering, why doesn't the baroreflex just fix this? Why do we have chronic high blood pressure? Why is that a thing? Well, it's because the baroreceptors become tolerant. This is known as impaired baroreflex sensitivity. So I'm not going to go too far into this, and we can talk a little bit more about this during the Monday session, but there are a lot of detrimental side effects and consequences of hypertension, all right? Most the top 3 of them I've listed here, which is damage to the arterial walls. So you could have stiffened or narrow vessels with arteriosclerosis. You could have enlarged vessels because there's so much pressure always beating on them that they become a little bulged. This is termed as aneurysm. Or you could actually have those vessels leak or rupture. This is termed hemorrhage. Or you could have endangered heart health. So when the heart has tons of increased chronic pressure, the heart muscles actually grow and thicken in order to deal with that constant high beating and high pressure. That thickening of these ventricle walls is actually bad because the vessels that feed the heart can't keep up with the nutrient reserve that is required to feed such a large heart. We're just anatomically not built to have an enlarged heart because we can't nourish it the right way. And then you can also have disrupted circulation. So this is mostly because of all the vessel damage, but you can also have the specific disruption in circulation based on the potential for a cardiac arrhythmia or fibrillation, which happens with damage to the heart. Or you could have an inability to exchange nutrients and oxygen or other gases properly, and you can also have blood clots that block blood flow that form because of those plaques, and this is known as thrombosis. All right, so the overall take-home messages that I want you to have from this is to understand and know the direction of blood flow and Ohm's law, understand blood pressure readings, the systolic versus the diastolic, understand the main ways that blood pressure is regulated by the body, and understand why high or low blood pressure is bad. As always, come with questions, anything that you didn't understand as well, to the Monday session. That's going to be on October 11th. And there's another video that is really great and short and sweet that will really help you understand all the content that I just went through. And I will see you in class.